Hello, my name is Nick Harvey. I'm here with my colleagues Juan Jamali, Caleb Estelle, Yazabeth Guerrero Gomez, and Julia Zach, and we're doing a presentation on the analysis and redesign of a meat grinder. So a meat grinder is a machine that processes raw animal meat by breaking it down with the use of sharp blades and a hand crank. So some of the primary customers will be butchers and supermarket meat departments who are trying to sell meat products to consumers in packages. And the secondary customer would be restaurant chefs and at-home cooks. They are more trying to make meat products from scratch and make their own meals. Here's our CAD drawing for the meat grinder. At the top you can see the hopper, and the middle part is the grinder itself with the hand crank, and then the meat comes out of the extruder at the end. And the bottom is the table mount, where it would just be mounted on any sort of table. Here are the labels for all of the different products, or all the different parts that go into a meat grinder. We use these for our analysis of cost and everything, and for our redesign.
The FAST diagram illustrates how the primary function of the meat grinder is broken up into sub-functions which guide our design decisions. The main function of the meat grinder is to grind animal meat. We then ask the question, how will our grinder achieve this? This can be done by inputting, cutting, and extruding the meat. Some of these sub-functions are broken down further, which ensures that we explicitly state each terminal function. The four functions which are present in every FAST diagram are shown in red. In order to assure dependability, we must engineer the grinder to prevent injury by enclosing dangers and making it easy to control. The grinder is more convenient when the cleaning process is streamlined, and the product is enhanced when we include a way to control the granularity of the meat when it is extruded. The function component mapping matrix is a way for us to map each function from our FAST diagram to a component on the grinder. This ensures that each component is serving a purpose and that each function of the grinder can be fulfilled. One part to notice is the streamline cleaning function. Every component in the grinder must be engineered for ease of cleaning, since cleaning up raw meat is critical to food safety. Additionally, even a single hard-to-clean part can ruin the purpose of the grinder by harboring bacteria. From our analysis, we see that each part we have identified is serving a function and that every function is being covered by at least one component.
Two different assembly sequences were identified as feasible for this product. The major differences between the two sequences lie within the order of the subsystem's assembly. In sequence 1, after the barrel is assembled to the hopper, the shaft subsystem is assembled, followed by the cutter subsystem, then the crank subsystem, and finally the clamp subsystem. In sequence 2, after the barrel is assembled to the hopper, the clamp is then assembled, followed by the shaft subsystem, then the crank subsystem, and finally the cutter subsystem. When compared to one another, sequence 2 scored higher than sequence 1, with a score of 12 points compared to 10 points. Sequence 2 is identified to be easier to locate the parts, easier to fasten and join during assembly, and easier to test the subassemblies.
Hi, this is Juan. Here you can see the bill of materials for the meat grinder. So we started by looking at each part and whether that part was directly in contact with food or not, and the durability we needed for that part in particular to decide what material to use. In the case of the parts that are directly in contact, we went with stainless steel and polypropylene for the plastic parts. From there, we decided on the manufacturing processes required and then assembly processes. From the volume, density, and the cost per weight, we estimated the material cost and then the processing cost, assembly cost, tooling cost, and finally the total unit cost, considering a batch production of 50,000 units. From here, and considering the functions of the product, we analyze each part using the what chart to decide whether to keep as it is, eliminate, or redesign the different parts. And we decided to redesign with DfM the crank, hopper, clamp screw, and barrel, as well as eliminating the lock.
After creating a function differentiation table for the primary customer group, being the butchers and supermarket departments, and the secondary customer group, restaurant chefs or at-home cooks, we determined the function differences between each customer group was the amount of meat contained in the hopper and the granularity of the ground meat. Here we are comparing the component platforms and modules. On the left under platforms, we have components which are shared by the designs. The modules are differences in design, in our case, the screw conveyor and extruder plate. The first module is a screw conveyor which guides the meat in the barrel. For the primary customers, being the butchers, the screw conveyor is made out of a stainless steel for industrial and food grade compliancy versus a polypropylene material for the secondary customer group, being the at-home cooks. The second module is the extruder plate, which ultimately shapes the ground meat. For the primary customer group, the holes in the extruder plate were redesigned to have a larger diameter for a more coarse grain, while the secondary customer group has a smaller diameter hole for a finer granularity. Delayed product differentiation is ideal for assembly in the manufacturing process. In this figure, we can see that by pushing back and adding the screw conveyor after the attachment of the shaft, we are able to optimize assembly efficiency.